In this video, we solve problem 6.1.8 from Nagle's Fundamentals of Differential Equations, 7th edition. We're asked to determine whether the set of functions is linearly dependent or linearly independent on the specified interval, and we're asked to justify our decision. This problem actually appeared in the differential equations class on quiz number 4 during the spring 2021 semester. Everyone received a different quiz. Some students saw this problem. Now, there are a couple of ways that you can go about answering this question. You can think about linear independence and linear dependence in terms of that equation that defines a set of linearly dependent functions, or you can use the Wronskian. I'm going to show you how to do both ways, and I'll show you that you get exactly the same thing either way. So let's start with the Wronskian of these three functions. So the way we do that is we put the three functions in this top row, and then we evaluate a 3x3 determinant that comes from taking the derivative of each of these guys twice. So I'll take the derivative of this once, and then take the derivative again, and take the derivative of this once, take the derivative again, take the derivative of 2, we get 0. And of course, if we take the derivative again, we get 0. Now, whenever you're evaluating a determinant, you can expand along any row or column you want. So the easiest computation comes from expanding along columns or rows that involve as many zeros as possible. So as soon as I saw those two zeros, I'm like, I want to expand along that column. Now we have a sign convention to figure out the appropriate sign that these factors need to be multiplied by before we multiply by a corresponding 2x2 determinant in order to evaluate the 3x3 determinant. We always start over here with a plus. And then you alternate signs as you go across the row, and then wherever you ended up, you pick up where you left off over here. So we would say plus, minus, plus, and I'll write down this one, minus, plus, minus, plus, minus, plus. It's really important that you do that. If it was a 4x4, it would be plus, minus, plus, minus, plus, minus, plus, minus. The size of the matrix matters. It's not always just sort of plus, minus, plus, minus, plus, minus. It doesn't always like sort of alternate signs as you go down rows and down columns. It's only when the number of rows and columns is odd that happens. So we're here, and you could put the signs everywhere, but the only signs that we're really interested in are these signs on this column here if we're going to expand along this column. So this Wronskian can be computed by taking positive 2 and multiplying that by the 2x2 determinant that comes from crossing out the row and the column containing that 2. So we're going to cross out this row and this column, and we'll have the 2x and the 2x and the 2 and the 2 in the second row. Minus 0 times some 2 by 2 plus some 0 times the other 2 by 2, but multiplying anything by 0 doesn't do anything. So this is just going to be a 0 here and a 0 here. And then over here, we're going to have 2 times the value of this 2 by 2 determinant. So you're going to multiply across that diagonal and subtract. So we're going to have 2x times 2 is 4x, and we're subtracting another 4x. And of course, 4x minus 4x is 0. So that means the functions are linearly dependent. And that's true for the interval from -infinity to infinity. Now, another way to show that these are linearly dependent is to think about the definition of a linearly dependent set. So here's the definition. We say that three functions, f1, f2, and f3, form a linearly dependent set. I'll just use LD for linearly dependent on some interval I. If there exist constants, C1, C2, and C3, not all 0, such that C1 times F1 plus C2 times F2 plus C3 times F3 equals 0. Now, if we're saying that they're not all 0, what that's telling us is that, let's just pick F3. The F3 can be found as a linear combination of the other two guys. This idea of linear dependence or linear independence is dealing with whether or not there's a function on the list that is redundant. So question is there a function on this list that is redundant? And I think you can see, like, yeah. Question is there a way I could take a combination of an x squared and a 2 and get an x squared minus 1? Well, sure, if I take one of these and I subtract half of that, well, then I'll get one of those, because half of 2 is 1, and I'm subtracting. And so, yeah, this is definitely linearly dependent if I'm just thinking about the definition of that. So with that in mind, we can answer this question without computing the Wronskian, although the Wronskian does confirm what we know to be true. It's easy to get as x squared minus 1 from these two. You just take one of those and you take half of those and you add them together and you get that. Or this minus half of that and you get that one in the middle. Okay, so let's look at the options in MyLab Math and see how we might answer it based on those options. Okay, so these are the options that we have. Now, all they have done here is they say the functions are linearly dependent because this equation has the solution C1 equals blank, C2 equals -1, so they gave you C2, and C3 equals blank. And instead of having an F1, F2, and F3, they substituted our first function x squared, our second function x squared minus 1, and our third function 2. And they're telling you they want C2 to be -1. So they're saying, let's look at this equation. C1 x squared minus the quantity x squared minus 1 plus C3 times 2 equals 0. So they've asked us to put a -1 here. So we can add this to both sides. And then just ask ourselves, okay, what values of the constants C1 and C3 should we choose to get this x squared minus 1? And it was just like I was telling you, if I want an x squared here, well, I need a 1x squared over here. So I think I'll choose for C1 to be equal to 1. And then if I want this C3 times 2 to be a -1, I guess C3 would just have to be -1/2 because -1/2 of 2 is -1. So I replace that there. So again, this idea of linear dependence and linear independence is about redundancy. You're saying, is there any way I could get this function by taking a combination of these two? I said, well, sure, take one of those and -1/2 of those, add them together, and you get that one. So that means this set is linearly dependent. One of these functions is not necessary. Now, if I just had the x squared and the 2, that would be a linearly independent set because there's no way I can get a 2 from an x squared, and there's no way I can get an x squared from a 2. They're not constant multiples of each other. So when you have two functions, the set is linearly independent as long as they are not constant multiples of each other. But when you introduce a third, what you're saying is, can that third function be written in terms of the other two? Or if there were 5 of them, you're saying, is there any function on this list that can be written as a linear combination of the other two? If so, then the set is linearly dependent. So we just said that C2 or C1 could equal 1 and C3 could equal -1/2. And if C2 equals -1 and we choose these guys this way, we'll get this function. So that is another way to answer this question 6.1.8 from the quiz number 4 in the spring 2021 semester.